In previous videos, I have used this little speaker as my power on self-test indicator. And I had added a little LM386 amplifier. It's the PPI number 1 that's actually generating that audio signal, sends it through the amplifier to the speaker. So I turn on my system, and at the end of my initialization code, I do a little double beep on that speaker, which my microphone usually does not pick up very well. As I'm thinking about doing a better job of power on self-test, there's a lot of things I can test. I have a couple of PPIs, I have a VIA, I have a math coprocessor, I have RAM. Maybe there's other things I can test along the way too. And I can write that to this LCD, to this 8-character display here. I could send it out through serial to my PC. And now I can use this little screen down here that I'm going to kind of use for post debugging. This is a little 128 by 64 for resolution. It's a little OLED screen. And I'm controlling that with I2C coming from my little Arduino Nano. So I can connect to the Nano through SPI from the system, and I can send it an SPI command and a parameter that goes with it. And I've now added support that for certain commands, I then pass on and write some information out to that screen. I'm going to go ahead and turn on my system here. And what you see is output here that shows that I've initialized, and I know the camera's not picking this up, so I will overlay a better picture of it. But it shows OLED initialization complete, or OLED init complete, RAM test pass, PIC1 test pass, PIC2 test pass, VIA1 test pass, Math Co test pass, and then it says post complete. So that's going to give me a better way to log, what specifically is being tested if it gets hung up on something, or if it fails, I invert this screen so it basically pops white instead of black with black text on it, and will give me details about what it is that I think failed. If there's something that fails before I even get to the point of having SPI support, though, then I can use my speaker because I have no visual output. Because this is SPI, this is SPI. I could use this LCD as one potential output if I don't even get to that point. And then that speaker, of course, both of those are going through this PPI, so chances are they're both going to work, or neither are going to work if there is an issue. I thought I would show you the code maybe that I've put in to support this, and really this is a start of a framework, so it's not done. You do see on this Terra term I am still sending output from here, and I can show when things are starting to be set up and what's happening. And this was that sample where I was reading back SD card data off this SD card. But now I can do things like, okay, I'm doing an OLED setup, and the setup of the screen was complete, and then I'm doing a print 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and a 50, whatever. Well, what I've done in my Nano code, if I pull that up, this is the code that's running on this Arduino Nano. So what I do is I've added in this library from Adafruit for an SSD 1306 OLED controller. This is actually a 1315, but it seems like this library works fine with the 1315. So 1306 or 1315, it's just this little display. It's 128 by 64. It has an I2C address, and this one I have addressed on 0x3C. Not a lot of options for that. On the back, there's a little, I think, a resistor I can change, desolder and move if I want to change that address, but there's not much for choices there. So I'm just using the default address of 3C. And then I've added in some additional commands that I can use. And so previously I've used this CMD print char, so I can send a command 1 to the Nano, followed by what character I want to print. Now I've added some OLED related, so I have a command 6 that is a reset for the OLED. I have a 7, which is a print char to the OLED, an 8, which is a print a status to the OLED, and then a 9 is just to clear the OLED screen. If I choose print status, then I've set up a series of different parameter values that I look for. So I can send it an 8, so a 08 followed by one of these numbers, and depending on which number I send it, it'll then print out different statuses to that screen. Or of course I can go back and do a print char from my assembly and I can send whatever sequences I want to send. I don't have to use predefined strings. In my code here, this is similar code to what I've shown before, where I get my SPI up and running. But then I'm going to get in here, I have my interrupt for my SPI, and in a previous video or two, the code I had in here, I was actually writing out to the serial output of that nano. So in previous videos in this ISR, I was actually writing out to the serial output so I could see it on my PC. And I had commented that that's not a good way to do it. It was just temporary. I was just doing some testing. I've now modified this so that when this interrupt happens, if it's the first packet in a series, I just make note of it and jot down what the data was of the command. That'd be the SPI command. And then on the subsequent packet, I know that that's the parameter data that goes with that command. And I jot that down along with the command, and I put it into a queue. So I've made a class over here that is a queue. And basically with that class, I can insert into the queue, I can delete from the queue, and I can check if it has anything in the queue. And now in my nano, what I do when the interrupt happens is I'm just going to throw something in the queue. I don't do any serial writes. I don't do any OLED writes. I do nothing that takes hardly any time at all. It's really just throw this in a queue. Well, then if I go all the way down to my loop code, in my loop, then I just simply say, well, if the queue has something in it, I need to process it. So then I pull out, I delete an item from the queue. This is a first in, first out. So the oldest thing in the queue, I pull it out, get the value, which is a word. So I've got 2 bytes of data. I then take the upper byte and send it as a parameter, and the lower byte and send it as a parameter to this process command. And that process command then says, okay, which command is it? Oh, you want to print CMD, or you want to print a status to the OLED. Okay, then which status is it? And then I can see I've got all these statuses penciled in here basically, so that I can say, well, yes, I'm going to go ahead and give it a status of 1 or 2. If a 1 comes in, that's my RAM test begin, and I'm going to write out to that display that the RAM test is beginning. And then when I get to a 2, then I know that that is a pass. And so this is how I'm now handling this. So I've got this process command. It just simply looks at something I pulled from the queue and says, what was the SPI command? What was the data that went with it? Like if I want to do a print char, which I've done in previous videos, I'm going to check, is it a print char command? And if so, what was the parameter? Because that is the character that I want to print out to the serial output. And if I go back to this, all of this data that got printed out was going through that queue and being processed this way, every one of these characters. So that queue seems to be working well. One of the things, just for awareness, if you're going to ever work with these little I2C screens, they must use interrupts in the background because you cannot, within an interrupt, write to them. You'll have problems with that. So if you're going to use one of these, make sure you don't try to write to it or work with it from within an interrupt handler or within an interrupt service routine. Do something like what I'm doing here, where you just simply take the critical data, get it into some array or queue or something, and then in your loop, when you're not in the middle of the interrupt service routine, then you can actually update the screen or do what you need to do. But I pulled everything out. So whether I'm doing a serial write or an OLED screen write, that is outside of the interrupt service routine at this point. If I go over to my 286 code real briefly, that code is pretty simple. So my code, it comes in here and I've got the start of it, which is this top is where my code starts. And in it, I then initialize my LCD and my PIC, or both PICs, I guess, as part of that, SPI, the SD card, this 8-character 7 segment I now initialize on startup. That was a bug earlier where this stayed on all lit up. I initialize it, I mark it as a low brightness value, and I just put in the dashes. So then I know it got initialized properly. But now I can put in simple calls to the nano, and I can say send it an SPI command followed by the parameter data. And command 6, as an example, is to initialize the OLED screen. And an 8 is I want to send a status to the OLED screen, and status 1 is RAM test begin. And then I do a finish and all this pick 1, pick 2, all the way down through these. And so what I'm going to actually put in next is actually do the tests. So I'll do the test begin message, and then I'll come in here and I'll call a procedure. And that procedure will probably be something like, let's see if this is the RAM, I might say test RAM. And I can do that call, and then if it passes, I proceed with this message, and if it fails, I give it a different message on the OLED. So that's I guess, how I'm stubbing all of that out or getting that working. The communications are all working, so now it's just writing some not really overly complicated assembly routines here that'll do the actual testing. Write to a register, read a register, write to a register, read a register, repeat that with all of these. So all 4 of these I can do that. Math coprocessor, I can actually do that calculation. If I press escape on my keyboard, I'm still doing that calculation area of a circle that I used in a previous video, and this is the result. So I don't need to display that anymore. I'll just simply, on the initialization, do the calculation and check for the known values. And if those are there, then I know that that math coprocessor is working. And if they're not proper, then I know it failed. You can also see when I hit escape, that's where I'm sending some different data, and I change the brightness level of this display. So that's I guess the way I'm going to start approaching some of this. Again, if there's failures before I can even get to the point of writing to SPI, then I'll have to use either my LCD to write those errors or beep codes. The beep code, that's only going to work if this PPI number 1 is working, and the chances are if that's working, I can also write to the LCD. So these two are kind of an all or nothing, whether I do a beep and or an LCD write on any early critical failures. That's what I'm going to do there. If I have something like a ROM failure, obviously this isn't going to get very far. I'm not going to be able to write to a PPI if my ROM isn't working or my RAM has serious issues. So I'll have to kind of learn how do I do some of those earliest type of tests and still show some output. Maybe it's an LED or something that's really simple as far as what I control. Maybe a couple other quick updates as I'm providing this video. As I mentioned, I did fix that bug on this when this was basically what I think was happening is this display I mentioned when I talked about it in that video isn't fully SPI compliant. And one of the things I found with it, that if the select line blips, so if it dips down and comes back up on this, it says, okay, what's my last set of data, and do that as a command. And what I was finding is that when I do a reset, I'm not sure where the blip is coming from. There is a blip though, and I don't know if it's when this VIA gets reset or initialized, or it's other SPI code causing it, but it causes a little blip, and then this says, oh, you want to go into test mode, and test mode, turn on all the LEDs full brightness, and then that would get stuck on, and you saw that in a previous video. Because I had no initialization code for this during the init. So I've now added that, so this will always come up. If I reset this, this will just come up with that nice dash, 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 nice and low brightness. And then I can see it went through my little posting messages over here again. Maybe another comment, my math coprocessor, I did get in some other math coprocessors. This math coprocessor is an Intel D80287-10. It's not a CMOS version, so I suppose it's an older TTL type version. I have a pair of AMDs that are the CMOS versions. They're P80C287-10s. I have tried these in here, and my system really dislikes them. And what I find is that when I'm running 12 megahertz into this system, remember the processor uses it at half that speed. The processor's running at 6, but 12 to this math coprocessor, the Intel one is fine with that. And there's actually a pin here I can change and tell it to use that full speed or use a 1/3 of it. And the Intel chip, even though it's rated at -10, it runs fine at 12, and it runs fine at 4, the 1/3. These AMD ones that are marked -10, they will fail if I try to send a 12 megahertz to it. And if I drop it down with that setting on that pin, they say run at 1/3, so it's going to run at 4 megahertz. they're still flaky. They just don't work. And it's not the chips. They're not the cause, but there's something in my circuit, whether it's because I'm expecting a higher voltage that I'm not getting out of these, or these have a faster rise times on the clock signal or the data signals. Something on these is different, and I don't know what it is yet. I've not spent any time troubleshooting it. I just need to get the oscilloscope out and do some debugging there. But these are causing enough of a headache that I just said, well, I'll just stick with this one here for now. It's working great, other than it's not a CMOS version. So that's maybe another quick update on here. You will also notice that I've pulled these jumpers for my hat on the processor. So I just got a jumper and I just said disable my output on my transceivers. So I have these transceivers that are going directly from address and data pins. My data pins here, my address pins here, to get to those LEDs through a resistor through these transceivers. Well, I set up the enable on a jumper so that I could, when I no longer want to use those, just disable them, because at 12 megahertz or 6 megahertz processor clock, they're pretty pointless. They light up, but they're not going to tell you anything at that speed. So I've disabled those, and the same with these. These are my external bus address and data, and at full 12 megahertz coming into the system, 6 for the processor, those don't add any value. So I've just pulled the jumpers on those in the same way. The way I've done these is the signals come in to the LED bar graph, to a resistor array, to a jumper, to ground. So if I just simply pull that jumper to ground, which is what I did, the circuit doesn't complete, basically. So those are now turned off. And if you're curious, this full system with all the LEDs, everything running, is running at about 1.5 amps. And right now I'm running 5.2 volts from my power supply into here. And depending on where I measure, whether it's up here, I think I lose about 10 millivolts just getting to the card. And I lose some in this card, and I lose some down the rails and some on the breadboard. But right now, worst case, that should get me to about 5 volts, or just shy of it at the worst points on this anywhere. So I think I'm doing okay power distribution wise. I took those off because it was just not necessary. Without those, I'm at 1.35 amps for this entire, what you see here. I think those are it for updates though. So I now have a new screen for post debug output. I've taken off some of my LED statuses. I fixed the bug on the SPI. Math coprocessor, I'll have to do some troubleshooting why the CMOS versions don't work. If anybody knows where I can find a non-AMD CMOS version, let me know. Everything I can find that is a CMOS version, the 80C 287, seems to be these AMD chips. And I can't find any others that are not AMD. I'd like to try another set just to see if there's something peculiar with the AMD ones, or if there is something in my circuit I need to adjust. So that's it. I am going to also have a video here very shortly about an updated system board. You probably saw my last video where that system board had some issues, so I have already designed up the update to that, and I will show that in the next video.